Today we're going to talk about basically word problems involving exponential equations. So I think, though, that I would like to begin with a preliminary issue, and that's the so-called change of base formula. So you may have noticed that on your calculator you only have a couple of logarithm buttons. Probably you only have log and ln. Those are probably the only logarithm buttons you have on your calculator. That is log base 10 and that is log base e. So the question arises, if you have logarithm base something else, like log base 2, how would you find a decimal approximation? How would you use your calculator to evaluate such an expression? The answer is the so-called change of base formula, and it says the following. Log base b of a is equal to natural log of a over natural log of b. So this formula allows you to rewrite any logarithm, log base whatever you want, in terms of natural logarithms, which of course you have a button for. If you ever have trouble remembering how this formula goes, just remember that the a is higher than the b on the left-hand side, and therefore the a should be higher than the b on the right-hand side. In other words, you may forget whether the formula is natural log of a over natural log of b, or whether it's natural log of b over natural log of a. Just remember that the a is on top on both sides and the b is on the bottom on both sides. So for example, if for some reason you wanted to get a decimal approximation of log base 3 of 2, then you would use this formula and say, oh, well, that's natural log of 2 over natural log of 3, and you can use your calculator to evaluate each of these and then get a decimal approximation. Okay, so with the change of formula out of the way, let's begin with, let's actually do an exponential equation, which we did some of yesterday, but I'd like to use this change of base formula to simplify the answers that we obtained. So here's an example. We have 2 to the 4x is equal to 5 times 3 to the x minus 1. So yesterday I said the procedure is take the natural log of both sides. So I'll do that. On the left-hand side, you might notice that the 4x can be pulled out and put on the side. So I will do that. Here, I made this comment yesterday. You have to be careful. The x minus 1 cannot be pulled out of the logarithm here, because what you have fundamentally on the inside of this logarithm is the product of two numbers. And so you have to rewrite this logarithm first as natural log of 5 plus natural log of 3 to the x minus 1. That is using the first log rule that I introduced a couple of lessons ago. Now the x minus 1 can be pulled out and put on the side, so I will do that. X minus 1 times natural log of 3. Now we just have to get the x by itself. I suppose that one thing you could do first is distribute the natural log of 3. 4x times natural log of 2 is equal to natural log of 5 plus natural log of 3x minus natural log of 3. To get the x by itself, of course, we have to bring all of the x terms to one side of the equation. So I will subtract this term from both sides. I get 4x times natural log of 2 minus natural log of 3 times x equals natural log of 5 minus natural log of 3. Now, in order to combine these two terms, you have to pull out the common factor of x. So I will remove the common factor of x. Oops. I'll remove the common factor of x from both of those terms. 4 times natural log of 2 minus natural log of 3 times x is equal to natural log of 5 minus natural log of 3. Okay. And now to get the x by itself, we just divide both sides by this expression here. So doing so will produce x equals natural log of 5 minus natural log of 3 over 4 natural log of 2 minus natural log of 3. As of yesterday, this expression was simplified or pretty close to simplified. There wasn't really a lot that we could do. However, there actually is something that we can do now. We can clean this up a little bit. So I'd like to try to rewrite this whole expression as a single logarithm as possible. And we actually can. So I'm going to condense all of these logs into a single logarithm. Beginning with the numerator, you have natural log of 5 minus natural log of 3. That can be rewritten as natural log of 5 over 3. Down at the bottom, I'm going to have to put the 2 on the inside before I combine these two logs. That's going to be natural log of 2 to the 4th minus natural log of 3. Then I want to combine these two. So this, of course, 2 to the 4th is, what is it? 2, 4, 8, 16. It's natural log of 16, right? So this is natural log of 16 minus natural log of 3, which is, of course, natural log of 16. With the change of base formula, we can actually rewrite this as a single logarithm. Let's recall again what the change of base formula says. It says log base b of a is equal to natural log of a over natural log of b. I'm actually going to read it in this direction. What I have now is I have an expression that is in this form right here. Natural log of one thing over natural log of another. And this rule says that I can rewrite that as a single logarithm. The base of the new logarithm will be b, the inside of the log on the bottom, of a, the thing on the top. So this can be rewritten as log base 16/3 of 5/3. And that's a single logarithm. Now, I mean, this is certainly fewer symbols, or it's maybe a little more condensed than this. I don't know that it necessarily is more illuminating. I have no more sense of what this number is than I do of this one. So it's kind of in the eye of the beholder, I suppose, which one you prefer. I will say, though, I do want to make one comment that there is a different way of solving these kinds of equations. I'm going to go back and rewrite this equation once again. So here's the equation we just solved. 2 to the 4x is equal to 5 times 3 to the x minus 1. I told you yesterday that you should always take you can always take the natural log of both sides of the equation. You can also take a different logarithm. You can take log base 12, log base 10, log base, whatever you want, and everything pretty much works the same. One comment that I want to make is that if you take log base either 2 or 3 in this equation, things work out pretty nicely. I'm going to take log base 3 and just show you how this works. If I take log base 3 of both sides of the equation, as you'll see, the work is reduced. So right now it's the same as before, and just like before, I'm going to say, oh, that 4x can be pulled down. 4x times log base 3 of 2 is equal to, and just like before, I have the product of one thing times another, so I have to write that as log base 3 of 5 plus log base 3 of 3 to the x minus 1. And here's where things get a little bit nicer. I'm just going to leave this term alone. I'm not changing anything. I'm just going to recopy that term. This term here, log base 3 of 3 to the x minus 1, exponentiating by 3 and taking logarithm base 3, they cancel. This expression is just x minus 1. Now, if you like, you can subtract x from both sides. So 4x times log base 3 of 2 minus x equals log base 3 of 5 minus 1. And then we can pull out a common factor of x from these two terms. So 4 log base 3 of 2 minus 1 x is equal to log base 3 of 5 minus 1. And then we can solve this equation by dividing both sides by this expression. I have x is equal to log base 3 of 5 minus 1 over 4 log base 3 of 2 minus 1. That looks quite different from the other answers that we obtained earlier, but it is correct. And I guess the point that I'm trying to make here is that these equations can be solved in multiple different ways. Oftentimes, if you take the logarithm base, one of the bases that appear in the equation, your answer will be simpler sometimes. But in other ways, it's sort of a disadvantage. I would argue that it is less clear how to simplify this expression into a single logarithm than the previous one. But I just wanted you to be aware that there are multiple ways of doing these. Okay, so as promised, this lesson is really, the thing that I really want to talk about is actually word problems. So let's get on to that. Let's talk about word problems. So just a few examples. So these are really just applications of the material we've been doing. So let's suppose that a radioactive element has a half-life of 2 days. And here's the question. How long does it take for the initial amount, the beginning amount, to decrease by, let's say, 20%. Okay? So here's what I'm going to do. I'm going to write down an exponential function which models the half-life, and I will use that to set up an equation, an exponential equation, and I will solve it using logarithms. So radioactive element has a half-life of 2 days. That means every so often we're multiplying by a half. So of course, being an exponential function, we know that it has the form y equals a b to the t. A is the beginning amount. We don't know the beginning amount, so I'm just going to have to leave a as just an unknown. B, however, we're multiplying by a half every so often, so we should write b as a half. So my model is a times 1/2 to the t. But of course, if you remember, we have this small issue where we sort of say, oh, we only want to multiply by a half every 2 days, right? This thing is supposed to have a half-life of 2 days, but right now we're multiplying by a half every single day. The clock is running too quickly. The exponent has to be modified. If we divide the t by 2, now we'll only be multiplying by a half every 2 days. So that's the idea. Okay, so now the question is, how long does it take for the initial amount to decrease by 20%? So here's the thing. If your amount of radioactive material is 20% less than what you started with, that means that the current amount of stuff that you have is 80% of what you started with. If you lost 20%, that means that 80% remains. So the current amount of radioactive material after the 20% loss is 80% of the original amount. Well, the original amount is A. So that means that the current amount is 0.8A, 80% of the original amount of material. And that's going to be equal to A times a half to the t over 2. Now, if I can solve this equation for t, that will tell me how long it takes to reach this point, how long it takes for 20% of the material to disappear. Notice that I can divide both sides by A, which is good because I didn't know what A was. It's a good thing that it disappears from the equation because now we only have one unknown, t, which is the thing that we're trying to find. Now, of course, this is an exponential equation. The t is stuck inside of an exponent. So what should you do? Take the natural log of both sides. I have natural log of 0.8 is equal to natural log of, well, the entire right-hand side. Okay. What happens next? Well, this exponent, t over 2, is going to come down. Natural log of 0.8 is equal to t over 2 times natural log of 1/2. All right, we're almost done. We just have to solve for t. This is a number, the 2 is a number. We just have to isolate the t. To get rid of the natural log of 1/2, just divide both sides by natural log of 1/2. So I have natural log of 0.8 over natural log of 1/2 is equal to t over 2. And then to get the t by itself, I just have to multiply both sides by t. So that's going to give me t is equal to natural log of 0.8 over natural log of 1/2 times 2. And you can use your calculator to find this and get a decimal approximation, because this answer is obviously not very illuminating. Okay, let's do one more. So one more word problem. All right, so here's my last example. Let's say an account, so like a bank account, has continuous interest, so continuously compounded interest. Okay? It takes, let's say, 10 years to triple. So every 10 years, the amount of money in the bank triples. So here's the question. How long does it take to quadruple? Quadruple, which means get multiplied by 4. All right, so here's the idea. If you have a bank account, right, and it takes 10 years to triple, here's what we can say. Every so often, you're multiplying by 3. So I'll start with the general exponential function. I don't know the initial amount, a. It doesn't matter. It turns out I won't need it. b, since I'm multiplying by 3 every so often, I'll make b equal to 3. A times 3 to the t. As usual, though, we should recognize that multiplying by 3, with just a t here, we're multiplying by 3 every single year. That's too often. We only want to multiply by 3 every 10 years. So we should divide that exponent by 10. And that's the correct model. So now we want to know, how long does it take to quadruple? Well, y, of course, is the current amount of money. If I want to know about how long it takes for my money to quadruple, when my money has quadrupled, that means I have 4a amount of money in the bank. A is the amount that you started with. If your money quadruples, then you now have 4a in the bank. So if I have 4a currently in the account, right? So replace y with 4a. I then notice that, as in the previous problem, a can just be divided off from both sides of the equation. So bam, bam, okay? And now I just have 4 is equal to 3 to the t over 10. And now t is the only unknown. I can solve for it by taking logarithms. So I have natural log of 4 is equal to natural log of 3 to the t over 10. As usual, this exponent can be brought down and put on the side. So that's natural log of 4 is equal to t over 10, natural log of 3. And now just solve for t. We have to multiply both sides by 10 and divide both sides by natural log of 3. So that's going to give me 10 natural log of 4 over natural log of 3 is equal to t. And, you should use your calculator to figure out what exactly that is. But this is an exact answer. Okay.